Okay, so in the previous lecture we started to look at the problem of constrained optimization, right? And the setup was as follows. We have this function f, right? This is the one whose minima we are trying to find out, subject to the constraints right. So this is what we had. So there were m equality constraints like so. Subject to those equality constraints being met, you have to minimize this function f and find out the point x star at which this minima is attained, right. In the process we came across certain terms, certain things such as tangent spaces, yes. So we said that the following has to be true. Suppose we haven't proved this part. We said that if a particular direction is a tangent direction, then it must be true that the dot product of that direction with the grad of hi at that point must be 0. But what we did not prove, but claimed rather, was the fact that if you find any direction such that its dot product with this gradient of these equality constraints vanishes, then those directions must also correspond to the tangent directions. We kind of gave a hand waving explanation and said that, well, you can think of this thing as like the small region zoomed in around this direction of feasible motions permissible by those H's while maintaining the constraints, and thereby you can think of it as a linear subspace, right. So if there are m constraints, then there are n minus m degrees of freedom, and those directions are exactly the ones that are given by the ones that is the orthogonal complement of these, provided of course that the point x star was regular, which meant that the grads of these hi's evaluated at x star must not be linearly dependent, yeah, they must span an n minus m dimensional subspace, so that their orthogonal complement is actually n minus m dimensional, right. So that is the intuitive understanding we gave instead of proving this. So we will say that this is actually, we will run with this ball and say that this is actually a characterization of the tangent space, okay. So V such that this actually gives you the tangent space, okay. So of course this is what we called as our D, perhaps I should use the curly D here, yes. This is our constraint set. So this was the setup, yes. This is just a refresher, just to jog your memory on what we have done so far, right. Any questions on this so far? Okay, great. So what are we going to now say? We have also seen another point about the function f itself, haven't we? What was it? Using the same mechanism, that is constructing a suitable g as an intermediate function in terms of the variable alpha, what was it that we saw? Did we also not see that this grad of f evaluated at x star, if its dot product is taken with what exactly? This fellow, this must vanish. And what exactly is this? In fact, this is exactly what led us or motivated us towards the characterization of the tangent space, because this object here sitting here is exactly that. It's an object that tells you a feasible direction of traversal while maintaining the constraints. So it's a legitimate tangent direction on the manifold, which is described by these equality constraints D. So combining these two, what do you think we might possibly claim? The claim, of course, again this is just a reiteration, the claim of course is the following, that for every feasible tangent direction, yeah, which is given by this condition, you must have that the dot product of the grad of f at the point x star with such tangent directions must be 0. In other words, these fellows must be orthogonal. Yes, geometrically this is the interpretation, but this is not very efficient in the sense that every time we want to describe a condition in terms of functions f and h, we have to talk about it as if in terms of these tangents. Can we somehow get rid of this tangent from this description and just talk about it as though we only require the f, the function, the objective function, and these constraints? Can we somehow come up with a condition that involves not a description of the tangent, that's of course there as a mathematical tool for us, but can we describe this condition succinctly merely in terms of the f and the hi's? And it turns out that we can exactly do that. And what's that description? What's that result that we are looking at? The result is this. Belongs to the span of okay. See, that's a neat little result here, because in this description you don't have to explicitly characterize any tangent spaces or even talk about these objects. You have the f given to you, you have the h, h1, h2, h3 till hm given to you. You merely find out the gradients of those fellows at a point, candidate point x star, which claims to be a minima, and at that point you should be able to express this fellow as a linear combination of these fellows. That's what it means. For a vector to belong to a span of a certain bunch of vectors, it means simply by definition that this is a linear combination of fellows here. Now this, because it's a regular point, is not just a linear combination of any arbitrary set of fellows, but a linear combination of a set of linearly independent vectors. Yeah. So this actually characterizes kind of the normals to your legitimate directions, right? It means that this grad of f must reside in the space that is orthogonal to the direction of traversal, exactly the point I was making the other day. So all of these grad f's, yeah, they should have almost a zero projection along the tangent, because if not, then if along one direction they are increasing, then along the opposite direction they will decrease, and that will violate the fundamental tenet of optimality or minimality in this case, right? So therefore it makes a whole lot of sense. Now this result, you might have seen it in some other form represented like so. Of course, it's just putting in technical terms the same expression as this, but we are more familiar with this. Yeah. So what we say is that there exist, these are the scalars, right? You can just push it on the other side and you get a minus sign. It's the same. So there exist lambda I star such that this is true. And those who have done a preliminary course on optimization at some level would immediately recognize that these are nothing but the Lagrange multipliers, right? So what we have essentially shown you, of course, subject to a small little gap here, that we haven't proved the equivalence of the tangent space here, we've just done it in a slightly hand waving manner, but essentially what we have derived here is the condition with the Lagrange multipliers. Now why is this interesting? If you think of this, how many lambdas are there? M of those lambdas. How many tuples are there in the X? N, right? So you can think of this as an expression that contains N X's, very loosely speaking, and M lambdas, right? So you can think of this as if you define this L as f of x plus summation lambda I hi x, right? But of course, what is implicit here is, what is this L a function of? Of both lambda and x. Yeah. So essentially, this is actually a function. Okay, this is not the best color. This is a function of both x and lambda, n plus m variables. Yeah. And if you now think of this as a cost function to be minimized, what you have is a condition for optimality in the unconstrained framework, isn't it? You have an n plus m tuple given by the x star and the lambda star, so that whatever appeared like a constrained optimization problem in n variables now appears like an unconstrained optimization problem in terms of n plus m variables, for the simple reason that the first order condition invoked on this L, written as a grad of this augmented unknown, that is x and lambda taken together, is exactly this, right? The first order necessary condition for optimality, for minimality, that we have derived for this constraint problem turns out to be the same as the first order condition for this unconstrained problem. So when you have constraints, just add lambda times those constraints to your original cost function and cook up the overall cost function as some L and invoke the first order condition on this unconstrained problem, on this seemingly unconstrained problem, and you end up solving the same constraint problem, right? So to go from a constrained problem to an unconstrained problem, the answer is given by the Lagrange multipliers. Okay, that's the reason why they are so popular, why they are so useful. Because you see, if you apply this now, okay, remember when you're taking the grad of this L, you're not just taking the grad with respect to x, but with respect to x as well as lambda. So the first n of those tuples here would correspond to the x's, the next m would correspond to the lambdas. So what do you have here? Yeah? You agree? What is the first? If you think of this, what does it give you? You treat the lambdas as constant, just the partials with respect to the x's, and what have you got? No, you have to equate it to 0. In other words, you have to solve for this, because this fellow immediately shows up, doesn't it? Right? So what you have is essentially grad of f. Okay, I'm dropping the arguments here with the hope that you already understand what those things are, plus summation lambda I grad hi. Yeah. What about the next m? each of the times if you just take a partial with respect to lambda 1, it just picks out grad h1. With respect to lambda 2, it picks out grad h2, right? Sorry, not grad h2, just h2, right? Because that's the L. So you have h1, h2, yes. So this first condition is of course exactly the same as this. If you solve for an x star and lambda star to satisfy the first condition, that's tantamount to solving for this. The next m conditions are of course tantamount to satisfying the constraints. So in fact, we've actually shown you clearly that the first order condition on this unconstrained problem given in terms of L is the same as actually satisfying the constrained optimization problem, right? So we'll see a couple of examples that you are very familiar with from optics, and we'll try to see the mind of light. What does light want to do? Of course, those of you who have done a course on physics, basic physics, which is probably every one of you here, you would immediately know that light tries to get from one point to the other in the smallest amount of time possible. It does not minimize the path length, it minimizes the optical path length. Yeah, this is particularly important for phenomena such as refraction. That's the reason why light bends, right? When you look at a stick below water, it looks bent. That's because the light from the tip of the stick below the water bends around the boundary and reaches your eyes, right? So we shall see how that can be formulated as an application of this, okay? Before that, we shall see a more basic result, which is reflection over arbitrary but smooth surfaces. Even that has everything to do with minimizing the time that it takes for light to traverse from one point to the other. Of course, here in case of reflection, the medium doesn't change. It just gets reflected from a surface and comes back at you, right? So we're going to look at those two applications next. So first, let's look at reflection. So we have some surface such as this, a smooth surface. So we are excluding surfaces such as these, so that if light bounces off from here, it doesn't know which way to go to. You understand, right? If there's a pointy thing like this, it's ambiguous. Incidentally, it's also got everything to do with the lack of differentiability of this surface, right? But in these cases, of course, locally speaking, you can draw tangents and treat them like flat surfaces, and you know what happens when light bounces off these, in what manner light travels thereafter, post reflection, right? We know that this angle of incidence and angle of reflection are equal, so we're going to try and see that. Suppose this curve is given by h of x is equal to 0. Yeah. Okay. Suppose there's a point here which is P1, and there's another point here which is P2, and suppose a beam of light hits this curve here at this point, which is say P, and then bounces back to the observer at P2. So the source of light is here, gets reflected off this point P and comes back to the observer here, right? So what is the total path length? Okay, so what we are trying to minimize is isn't it? Because the speed is constant. If you want to get to the shortest in the shortest amount of time, you just divide the length of the path by the constant speed. So whether you divide by the constant speed or not, the objective function only gets scaled. The value of the objective function changes. The point, the argument of the objective function at the point of minimization doesn't change. So we might as well run with this. So this is essentially what we are trying to minimize. Yeah, okay. If we take a grad of this object with respect to P, what do you think the grad is going to look like? Okay, just to be explicit here, let's call this x1, y1, let's call this x2, y2, let's call this x and y. So in fact, hidden inside that norm is the following. What is this tantamount to? X minus x1 whole squared plus y minus y1 whole squared under root. Yeah. And this by the same token is x minus x2 whole squared plus y minus y2 whole squared, the under root. So when you take partials with respect to x and y, what do you think turns out to be the result? Grad of f. Treat x1, x2, y1, y2 as constants, right? When you're taking a partial with respect to x, treat y as constant. When taking a partial with respect to y, treat x as a constant. So what happens? It's a square root. So you take the derivative, half will come out. This fellow goes down in the denominator. This fellow on the top. Chain rule of differentiation. So 2 times. So 2 and half will pulverize each other. Yeah. So one term comes out from here. One term comes out from here. When you take the partial with respect to x. So where do I write this? Okay. So what is it going to be? Yeah. And what about the other one? What about the denominator? I mean, sorry, not the denominator, the second term. So you have x minus x1 by, I might as well write this, no? In a mixed kind of a notation. Plus x minus x2 upon norm p minus p2. And this is going to be y minus y1 upon p minus p1 plus y minus y2 upon p minus p2's norm, right? Okay, let's hold this thought for a minute and let's also find out the grad of h, because what does our problem tell us? What have we just derived? That the grad of f at the point of optimality must be in the span of the grad of h. But the grad of h is just a single number, I mean a single vector, right? Because there's only one constraint here. Yeah. So what do we say then? The grad of h is the direction along which this must lie. Yeah. So this must be equal to some lambda times grad of h, isn't it? Agreed? That's what we've just derived. We're just applying that. On the face of it, this doesn't say much. But now, if I rewrite this fellow here in the following manner, x minus x1 by norm of p minus p1, y minus y1 by norm of p minus p1 plus x minus x2 by norm of p minus p2 and y minus y2 by norm of p minus p2. What can you say about these two fellows? What is a very interesting property of these vectors? Let's pull out this denominator common from here and this two denominators common from here. Does that ring a bell? What's special about these vectors? Sorry? They're unit vectors, fantastic. Now these are two unit vectors. So if you take two unit vectors, what can you say about their resultant? If you take two unit vectors or two vectors of equal magnitude, what about their resultant? The direction of the resultant. It must be the angular bisector, right? If you take two vectors of equal magnitude, then apply the law of parallelogram and the resultant is along the angular bisector of the two. But that direction must specifically be the same as the grad of h. What can you say about the grad of h on the other hand? Grad of h viewed locally is the direction of the gradient of this surface, which is the normal to it. So what then does this tell us? Haven't we derived the law of reflection already? If you look at this curved surface, look at the normal, that normal must be along the angular bisector of these fellows. In other words, the angle of incidence is equal to the angle of reflection. Follows as a consequence of what we have just derived. You also see the importance of why we wanted this to be smooth enough, because we wanted to have a well-defined gradient of this h. If you have really sharp edges like on a cliff or something, you wouldn't know which direction light's gonna actually get reflected along, because the gradient isn't well defined. But as long as the gradient is well defined, that gives you a local picture. You can think of it as locally as a flat mirror. If you do that, then you find out the normal to it. That normal direction must be exactly the angular bisector of these two rays, one the incoming one from the source of light and the other the outgoing one after being reflected from the surface, which essentially proves the law of reflection, because this right here is your grad h, right. So we have essentially proved the law of reflection using this idea that we've just developed of Lagrange multipliers. Of course, as you might have noticed, this did not really involve us actually finding out what the values of the Lagrange multiplier are. Just the geometric interpretation and understanding of this led us immediately to that conclusion. Okay. Next we shall see that even the law of refraction, right, which you are all familiar with, that can also be derived using this same idea that we've just developed of optimality, and knowing that light is always trying to get from point A to point B in the shortest amount of time possible. Okay. So that's what's going to come up next.